So we graphed two parabolas on the board, and because you guys know transformations, you knew where this parabola went, and you found that its vertex was -4 and -1. And then with this one, we used transformations to move it to the right 2 and up 3, and you found the vertex was 2, 3. So do you see a pattern here?
Yeah, you just change the symbol of the number that's in the parentheses and then add on the ending number.
Yep, so to find the vertex, if you have a parabola in this form, if we have a quadratic equation, we'll talk about what those are in a minute. If you have a quadratic equation in this form, it already has the vertex in it. It's actually called vertex form for that reason. Okay, so we're going to talk about quadratic equations, or quadratic functions now. So you may or may not have seen these in Algebra 1. So a quadratic function is any function that can be written in this form, ax squared plus bx plus c. So all these red ones are like not in your notes, so you can like write those down if you want, all the red words.
Oh.
Yeah.
So we actually do function.
Make you do a little bit of work, right? Or just make you at least look up and copy red words down. One of the two. Okay, so a quadratic function is any function basically that has an x squared in it that can be written in that form. Oh, and where the coefficient a is not equal to 0, which is kind of a given because if a was equal to 0, this whole thing would be 0, and then you would just have a line, right? So if we just have x in it, it's a line. If we have x squared, it's now a quadratic. So all quadratic functions are transformations of the parent function. So you guys remember the parent function that we just graphed, right? So I want you to think about this. I'm going to move this for just a sec and then we'll come back to it. Okay. So if I have a function here, remember that little function machine I had where it like this, you put in a number and then something happens and then it spits out another number. Well, if I have this function, x squared, and I put in 1, what comes out? Okay, what if I put in 2? What if I put in 3? And 4? Okay. So if this is our parent function x squared, and if I wanted to graph it, I could use a t-chart just like this, and I could say, all right, now what is this going to actually look like, right?
Yeah.
So when x equals 1, y equals 1. Okay, we'll start with 0, 0. X equals 1, y equals 1. When x equals 2, y equals 4. So it's like up here. When x equals 3, y equals 9. So it's like even more up here.
That's how I do it in Spain.
Yeah, you do it like a t-chart? Yeah.
I do like that.
So this is, you guys, I know you did this in Algebra 1, but it's been a long time ago, so you might not remember. But you can graph anything with a t-chart. You can have literally any function, and you can just imagine it as this like function machine, right? I put in an x, and it spits out a y. It does something to that x, and it changes it into the y. And so you can graph literally any function by doing this. It's not always easy, because sometimes functions are really hairy, but what we're going to do is we're going to learn how to graph these parabolas without having to do a t-chart every time. So this should be like a lot more. This should look prettier down there. But that's basically the parent function of this. Starts at 0, 0, and then it goes up 1 over 1. And for the second point, it goes over 2, up 4. See that? See how that makes sense? Because, you know, we're just squaring numbers. Okay. So basically, all quadratic functions are just transformations of that original function, right? So that's our parent function. That parabola is our parent function, and every other quadratic that we work with is just going to be we're just going to move that original function some way. We're either going to shift it, or stretch it, or flip it, or do all of those other things, but all of them are just transformations. Okay, so you figured out with our activity at the board, if it's written like this, x minus 8, if it's written like x minus some number squared plus some other number, that this inside number is the x coordinate of your vertex, and the outside number is the y coordinate of your vertex. Okay, so this is just what it's called vertex form. And we use h and k a lot. H usually means the horizontal shift, and k means the vertical shift. I don't know why they use k and not v or some other letter, but they did. So, this is vertex form. So what would the vertex of this parabola I have right here be?
Wouldn't it be one above it? Or wait, I'm kind
So vertex.
Oh, that's an example of vertex form.
Yeah, so this is an example of vertex form. So if I had this parabola, what would the vertex of it be?
Hang on, I'm thinking.
You're thinking.
It's getting there.
Think about our examples up here that we had. So see this example?
I got it, I think.
Okay.
Okay. So then it would be -2 and 2, right?
Very, very close. It would be positive 2 and 2
because
and
x is always a liar.
X is always a liar. So x
Then
lies.
x.
So the vertex of this one would be at 2, 2. So you could actually graph that, right? You could just put a dot at 2, 2, and then you can start your parabola. Okay? So my question is, what does this 4 do to things when it's outside of the x? What does it do? Yes, it multiplies. So what does it change? How does it change our graph?
It would change your slope, wouldn't it? No.
Yeah.
It wouldn't just make
Well,
your
it
graph
would-
quite a
it would
bit
stretch
bigger?
vertex.
Wouldn't it just put your graph on a bigger scale?
Yeah, it would stretch it.
Yeah.
So it'd stretch it. So remember, if you look at that pink sheet you have, that number in front, stretch it. It gives a vertical stretch, which basically, and you could write this down, this multiplies all your y values by 4. So that's a vertical stretch. So when a minute ago Cole said that it's your slope, and on a line it is your slope, right? Because your slope is the same on a line every time. And you can kind of think about this as a slope, but parabolas don't, you'll learn in calculus, because you're all going to come to calculus with me, yay! You'll learn in calculus that parabolas don't have, they don't have a single slope, right? Because at the first point, at this first point we went up 1 over 1, and then the second point we went up 4 over 1. So our slope is changing. So but you can kind of think about it as the slope of those first points. So from your vertex, if you have a 4, instead of going up 1 over 1, you'd go up 4 and over 1 for your very first point. Right? It doesn't keep working for the rest of the points, but it works for that very first point. Does that make sense? So let's try to graph. Okay, let's try to graph some parabolas. Actually, let's see if there's anything else. Okay, A determines the direction of the parabola. Oh yeah, what if A was negative? If we have negative in front of the parentheses, what does it do? All the y's would be negative, and that flips it like this, right? So if you have a negative A, your parabola is going to open down. If you have a positive A, it's going to open up. Okay? It also determines whether it's stretched or compressed. H gives us which way we go left and right, and K gives us which way we go up and down. We already know that. So let's practice. Okay. First, we're going to figure out how it's transformed from the parent function. We'll graph the parent function, and then we're going to graph the new one. Okay, so let's start by graphing the parent function. So the parent function starts at 0, 0. And our first point on the parent function is up 1 over 1. Right, because 1 squared is 1.
Wait. Oh. Wait, I'm confused on what to do with the 1 over 2.
That'll tell us the stretch. So we'll look at that first. We're gonna graph the parent function first, and then
Oh, okay.
this is gonna tell us the stretch or compression.
So you're just doing like the x plus 2 squared, right?
Well, right now I'm just graphing y equals x squared.
Oh.
So I'm just gonna graph y equals x squared because that's our parent graph, and then we're gonna transform it. Okay, so our parent function goes up 1 over 1, and then up at a 4, 1, 2, 3, 4, and over 2. Do you guys understand where I'm getting those points from?
Yeah, didn't you just times 2 by, or you just square root of 2?
Yeah, I squared every one of my values. So when x equals 1, I squared it and it equals 1. When x equals 2, I squared that and it equals 4. So that's why I put that point there. And x equals 3, 1, 2, 3. 3 squared is 9. 2, 3, 4, 5, 6, 7, 8, 9. Oh, I do have room. So
it's basically you just, I think I'm starting to get the hang of it.
this is the parent function. This is beautiful, I know. This is the parent function for quadratics, okay? Now let's see what happens when we do this stuff to it. So what does the 2 inside do? Yep, it moves it -2 in the negative direction too. So it would now move it to here, right? So I'm gonna kind of just like sketch that one there, because that's the first thing we did. Okay. Now what does the negative in front do? Yep, it makes all the y's negative, see, because it's outside the parentheses, so it doesn't change our x's negative, it changes our y's negative. So it flips it the other way. So now we basically have this. Okay, so this is transformation number 1, this is transformation number 2. And the final one we need to figure out is what does that 1/2 do?
No. So
It makes it fatter. It gives it a vertical compression. Because what we just did is we multiplied every y value that comes out by 1/2. So normally
It's just gonna be flat.
Normally I would go up 1, or I would go like over 1 and up 1, you know, right here. Right? Instead, my y value is going to be multiplied by 1/2. So I'm going to go over 1 and only up 1/2. I'm going to over 2, I'm going to only go up to 2. Because this one is 4, so here are my points. 1, 1, and 2, 4, and 3, 9. This half multiplies each one of those by 1/2. So my new points would be 1, 1/2, 2, 2, and 3, 9/2. Just like 4.5.
Oh.
Okay.
So you don't times the x value, but you do
Right. It
times
doesn't change
y.
my x values because see it's outside of the parentheses. Yeah.
And then because it's flipped, does it have to go? Did the y have to be negative?
Yes. So that flipped changed all of my y's negative. So then our actual points. Oh, and then they moved to.
So I'm kind of confused on where we like got the
So you have to take your x
from.
to -2. So subtract 2.
Yeah. So yeah. So we could do this with algebra or with a graph. Awesome. Okay. I kind of did a like graph here and algebra here. So let's mix and match. Okay. Let's do algebra from the beginning. First transformation I did is I moved all of my x's over 2, right? So we're going to take all of our x values and we're going to subtract 2 from them.
So then where does it tell you that like you have to do that or like move it over to? Or did you just choose to do that?
This right here, that 2 in there,
Oh, okay, because
tells me I have to take all of my x's and move them 2.
And then
Now
as
see
far
how-
as it like reflecting over the x-axis?
This negative sign right there is a reflection.
Okay.
So what that negative says is I need to make all of my y's negative, right?
This is gonna be a disaster for me, I feel like.
So the next thing is I would just make all of these negative. Okay, so that's to this graph right here. We're right there. And then we half all of our y values. Okay? So we're going to half all of these, and our final points for our final transformation would be 1, negative 9/2, 0, negative 2, and negative 1, negative 1/2. So let's graph those. So we know our vertex stays here. That's 0, negative 2. Hang on. Oh yeah, I understand. I was like, where did I couldn't remember where I got my 0 from, but I remember now. Okay, and then 1. Let's see, negative 1, negative 1/2. So it's this one right here. Right? So it's like squished. And then at 1, oh wait, sorry, that's 0. That's and then at 1, we're at 9/2. 1, 2, 3, 4 and a half. So it just got wider because we compressed it vertically.
What do you do with the 0, negative 2? This is that 0 and you don't.
This one's actually this one. Sorry. The 0, this one I didn't actually list as one of our points, our 0, 0. And so I just like knew that's where our vertex would be because I looked at the graph, but I forgot to list it with our after one. So 0, negative 2 is this one right here. It used to be this point, then we moved it over, and then we flipped it, and then we divided. No, it used to be this point right here.
Can you kind of explain, so the parent of a function, is that just basically like your x value?
The parent function is like the original function before we move it or change it or anything. So we have certain parent functions, like y equals x is our parent function for lines, y equals x squared is our parent function for quadratics, y equals the absolute value of x is our parent function for absolute values. So we have lots of parent functions that we're going to learn about this year. And this just happens to be the parent function for quadratics. This is the original parabola.
So then y equals x squared will always be the parent function?
Yes. For a parabola, that's always the parent function. And then
I
all
was
we
just
do is we change
confused
it.
on like where we got it from. I thought we pulled it out of the equation and I was like, huh?
Yeah, no, since this is a parabola because it's squared, it's always, the parent function is always going to be y equals x squared. All right, let's try to do this one just graphically and see what we can do. Okay. So we can take the parent function and we can graph that one. Okay, so there's the original parabola, right, before we do anything to it. And then we can start moving it. So we're going to move it right 1 and down 3. Do you agree with me there? Right 1 and down 3. Okay. So I'm going to go over 1 and down 3. 1, 2, 3. So right here. So here's my kind of translated one. Move it there. And then finally I'm going to take that 2. That means I take all of my y values, I multiply them by 2. So it's like a stretch. The last one was a compression, this one's a stretch.
So then, I understand that you moved it down 3 because there's that negative 3 on the end. And then what would say go right 1?
That 1 in there with the x.
Okay, yep.
Yep.
Because
Yep, because it's funny, so it's gonna, that tells us to move to the right. Okay, so the last thing we're gonna do is, remember the first point normally on our parabola is up 1 over 1. So now we're gonna go up 2 over 1 instead. Okay, so from our vertex, up 2 over 1. And then our next point, we normally go up to, or no, sorry, over 2, up 4, because 2 squared is 4. So we're going to go over 2, up 8 from our vertex. We're going to go over 2, and we're going to go up 8. Okay, so this is the difference. Do you see how they look different? Do you see how we moved it, but then this one actually got squished quite a bit, like not squished, it really got stretched vertically. So it got stretched, and that's what that 2 does, is it stretches it. So if you saw it, if you looked at it before, okay. Before we moved it, the blue one is our parent function, the 2 stretch is our parent function. And then we shifted it left, or right and down. Okay, let's practice a few more. Yes, do you have a question?
Well, not anymore.
Okay. All right, so let's look at the next one. Can you tell me what the vertex of this first function is? So we could draw the parent function and we could move it and do all of that, but do we have to do that? What's the vertex? It's at 3, 4, right? Because our vertex is right in the equation. So we can just say, well, here's our vertex is 3, 4. So then I go over to 3, 4. 1, 2, 3, if I can count. 1, 2, 3, 4. There's my vertex right here. Now, does this one face up or does it face down?
Up.
Up, because it's a positive number in front of here. Okay. And is it the regular, like just up 1 over 1?
Nope.
Nope.
It's going to be skinnier because it's got a 2 in front.
Yep, it's going to be skinnier. So we go over 1 and up 2 instead of over 1 and up 1, right? Over 1, up 2. So we go over 1, up 2, 1, 2. Over 1, up 2. Over 2, 1, 2, and then it would be up 8, which is like way up here. So we're just gonna wing it on that one. Make that beautiful parabola right there. So you can graph the parent function and do all the transformations, but when it's in vertex form, you can graph it without even having to transform, without even having to do all those transformations in your head.
You know what I just realized? Like,
What?
I know exactly what you were trying to tell me earlier, because like when you're finding your new points, you know how you said that, like you just kept doubling? I was super confused by that, and then I just realized that you can literally just double points.
Yep. No, it takes a minute to marinate, right? I tell you something, and then you sit on it for a minute, and then it like, you get it. Okay, here's one more concept that I want to talk about with these parabolas. These parabolas are symmetrical, which means that you could cut them in half, right? And you could just like fold them over onto themselves, right? So where is the line or the axis of symmetry for our parent function? Let's get this one on first.
Ooh.
Where?
I would say.
Okay, finally. Yeah, where's the line?
It's going to be on the y.
Right, so this would be this on the y-axis. This is our axis of symmetry, right? If I folded this parabola in half on that line, so the axis of symmetry is also the x-coordinate of my vertex. Let's see if that works for all parabolas, right? Because my vertex is at 0, 0,
Well, it probably wouldn't work for all of them because, like, what would happen with the one that we just did?
Well, let's look at this other one that we graphed really quick. Where's the axis of symmetry for this one?
Wouldn't it be 0, 1?
So the vertex is at, let's start with that. The vertex is at 1, -3. That's where the actual vertex is, right?
Oh, right.
And then the axis of symmetry for this one goes right down the middle of this parabola. So the line that gives us our axis of symmetry would be x equals 1. The axis of symmetry would be x equals 1. It's the line that I could fold this parabola in half on.
So then with the 0, could you do x equals 0? You have to have like...
Yeah, no, so axis of symmetry is a line. So we should write axis of symmetry like that,
Okay.
x equals 0. Okay, so let's see if it works for the one that we just graphed. X minus 4 and x plus, or x minus 3. Okay, so we just graphed this one. Is that the right one? Minus 3 plus 4. Okay, we just graphed this parabola, right?
Yeah. Yeah, I think so. It
Hang
looks
on,
like
it's
super
not quite right.
far away.
Yeah, I put something in not quite right.
Here, I can...
I squared the 3 instead of...
Oh, instead of putting it on the outside there.
Yeah. There we go. That looks better?
Yes.
Okay.
So then, your axis...
So let's start with our vertex. What's our vertex on this one?
Vertex would be 3,
4. So our vertex is at 3, 4. What's our axis of symmetry? What's the line that we could fold out of?
It's going to be x equals 3.
You guys agree?
Yeah. So tired.
Yes.
Easy.
I know. It's only Wednesday. Oh.
Yeah.
The vertex is easy to find, and then the axis of symmetry is just whatever it's like x equals, and then whatever the vertex, the x coordinate of the vertex is. Does that make sense?
It's like the only thing that's made sense to me, like, ever in this class.
I know. It's like slow, it just takes a minute to sink in. You'll get it. Okay, so let's look at this one and figure out what the vertex is of this one. What's the vertex?
-4, -5.
Yeah, vertex is at -4, -5.
So then,
Would this one face, would that one face up or down? Down, okay. So we could even say concave down. That's our math terms. That means that it faces
do
down.
both of them have to be negative or just the x? To make it a concave down.
To make it concave down, neither of these matter. This matters right here.
Oh, that's right.
Right, so this is positive, so it's concave up. This is negative, concave down. And then, what's the axis of symmetry?
Wouldn't it be -4?
Yep, x equals -4.
Which really, you don't even have to graph that out, honestly. Like, you could just get that from...
Yeah, so we don't even have to do like the whole transformation process. Like if you can't remember, then you can do that. But from vertex form, you could find all of this stuff, and then we could just graph this really easily, actually. Oh, I'm really good at this. I'm always messing it up. Okay. So I could graph this. I could put my vertex at -4, -5. 1, 2, 3, 4. 1, 2, 3, 4, 5. I know it's going to face down. And it has -1 in front, which tells me that I go over 1, down 1. So it's just like the standard parabola. It just happens to be concave down and at -4, -5. How do you guys feel about vertex form?
Not bad.
Not bad? So give me like a 1 to 4. 1 means I don't have any idea what you just said. 4 means I could teach it.
I'm gonna try like a 2.5.
Okay.
2.5 to a 3.
Good. Okay, we're gonna practice vertex form some more tomorrow. We have a couple more on here that we'll practice writing the equations. And then probably, we won't quiz on this until next week sometime.
I say we quiz on this as soon as possible.
Right, while it's still fresh in your brain.
Before I forget it, yeah.
I understand that.
I'm sure I will. As long as I keep up with it.